Right. Welcome back, everyone. I hope everybody had a good break, was able to get some coffee, get recaffeinated. Really excited about our next session here. We have Stefano, who's come to us from Germany via Scotland to visit us to talk about deep reinforcement learning for LLM agents and talk about current research in the area. Really excited to have our collaborators from the University of Edinburgh join us today. And so, Stefano, welcome to the stage.
Thank you very much, yeah. Okay, so first, you can hear me okay, right? Hands up if you can hear me. Good, perfect. Yeah, thank you very much for coming to the talk. So this talk will be about two parts. One is about deep reinforcement learning. In my group, we specialize very heavily in deep reinforcement learning. I want to share some very basic ideas with you. And then I'm going to make a pivot into some more recent LLM-based work and see what we can do there, share some observations with you, certain things that I think we may want to do differently. But first, let me introduce the group. So we are the Autonomous Agents Research Group at the University of Edinburgh. We are about 17 people at the moment, which is myself and PhD students and postdocs. And we very heavily specialize in machine learning algorithms for autonomous systems control. And also, we are housed in the School of Informatics. The School of Informatics is, by a wide margin, the largest CS department in the UK, with currently about 160 professors, and also ranked by the UK government as the #1 CS department for research power and impact. So we as a group, we try to create autonomous agents that can accomplish tasks in complex dynamic environments. So I'm showing a few examples that we're actively developing. On the left, you have warehouse automation tasks where there's humans and robots doing things together. We have self-driving. I was heavily involved with a company that was bought by Bosch a couple of years ago, and also various other sort of multi-agent tasks. So what all these applications have in common is that we have to build these highly capable autonomous systems that can take in a huge amount of data about the environment and make sensible choices in order to accomplish their tasks. The other thing that these examples have in common is that there's not just one actor, there are multiple actors that need to coordinate their actions in order to achieve something. So we develop machine learning algorithms and especially deep reinforcement learning to enable these systems to act. So there's two parts in this talk. We're going to go into the first part, which is about reinforcement learning. And I'll share some very basic ideas with you. I'm not going to bombard you with mathematical details. I'll keep it at a very high level. OK, so reinforcement learning, I think everyone here knows what that is. But we have a few sort of problem spaces in reinforcement learning that we care about a lot. One is about sample complexity and solution quality. So we want to learn as fast as possible and better policies. We are interested in learning control policies that generalize well. So when you make changes in the environment, the policy transfers. We are interested in multi-agent systems when there's multiple actors. It's very close to my heart. And also, I work with a number of various industry sectors developing applications where we take things from the lab into applications. So over the next few minutes, I'll take you through some of these verticals here and give you some basic ideas that may be useful for your own research and applications. So starting with robustness and generalization. OK, so now we're operating in a reinforcement learning environment where an agent is observing the environment through pixels. OK, let's say there's a robot that we want to control. We have continuous controls, and we get to see the robot through a camera. And in standard reinforcement learning, these policies that we end up with, they tend to be brittle. OK, so they heavily correlate against the pixels in the vision. And when pixels change, then the policy can fall flat and sort of get destroyed. Here's an example of what's happening. This is a classic inverted pendulum or a cart pole. On the left, we train an optimal policy. The idea is that you have to swing around to get the pole upright, and that works fine. But now we take the same policy and put it into the right image, which is where we only change the color of the line and the body, and the policy breaks down, right? It's doing something weird now. And the only thing that's changed is the color, nothing else. The optimal, the control strategy should be the same, but it's falling apart here. And so that makes reinforcement learning a bit brittle, right? We want something more practical. So the question is, can we learn more robust representations that generalize well? And the main idea I want to share with you is disentanglement that we've developed in a few publications last year. The idea is that we want to disentangle distinct factors of variation in the environment so that we get a more informative representation. And so what I'm showing here is in the middle of this image here, you have your picture from your camera, right? So this is the cart pole. This is what you see. And these pixels, they come from somewhere. There will be these ground truth factors. For example, there's floor color, wall color, object color, and so on. These are basically the parameters of the world, of the environment. Depending on those values, you then get your sensor input. So with standard RL, that's where you stop. You correlate against those pixels, and you end up with a brittle policy. We want to take this a step further and want to use the pixel inputs to disentangle, basically, and learn a representation that recovers these ground truth factors that generated these pixels in the first place. So we now want to have a representation where we identify that there is such a thing as floor color, wall color, and so on. And the benefit is that once we have that, if we take the policy and put it elsewhere, ideally, if only one or two things change, for example, the color as we just saw in this example, everything else in the representation remains well-defined, and hopefully we can gracefully transfer into this new environment. That is the idea of disentanglement in a nutshell. So basically, we developed that over a few publications. There's an interesting theoretical piece of work from 2019 that says that if you only use IID data, it's theoretically impossible to learn disentangled representations. But we showed in these publications that if you use the non-IID RL data, that is actually sufficient to in fact learn disentangled representations. So the first idea we brought out was in an iClear paper last year. As I said, I'm not going to bombard you with the technical details. Instead, I'm going to jump right into some results. And if you find this interesting, you can check out the paper, which is up on the slide here. So we call this first idea TED, which is temporal disentanglement. It's an auxiliary loss that you can connect with any existing RL algorithm, and it helps you learn these disentangled representations. Here are some results. Let me show you first what the setup is, and then I'll show you the actual curves. Okay, so we have a setup where during training, we experience a number of different of these ground truth factors, like values for different colors, for example. And so we get to learn, and then there's this vertical dotted line you see there, which is when we make a change in the environment. In other words, we get exposed to new colors that we never got to see, okay? In this case, it's colors that I'm showing you as an example. It could be anything else as well. And we tried this in a whole range of control tasks in different environments. I'm just showing you two examples here. One is the cart pole, and one is a walk-in example. And we tried this with a bunch of algorithms. So it looks like this. As you expect, you would expect to see learning at various degrees, and then there's the change in the center, and everyone sort of begins to is in this new environment, and there's a degradation in the quality of the performance. But what we can see in the blue line, which is the one that algorithm that uses TED, it's actually much less so affected than the other algorithms. The other algorithms have a huge drop, and sometimes they also are unable to recover. Whereas with the blue line, you can see that we are able to recover, and we don't have as much of a drop. So that's nice. The other thing too is you can actually measure the disentanglement score, where 1 is the highest you can achieve. That's the ideal outcome, so to speak. And you can see that if you use this auxiliary loss, you're much closer to a disentangled representation. So that's nice, but that's just the first step, and there's more that could be done. You can see that it's not quite perfect, it's not quite there yet. And we didn't leave it there, we took it then to the next step, which is that there's in fact correlations in these ground truth factors. TED, which is this first thing I just showed you, assumes independent ground truth factors. But in reality, in reinforcement learning, you tend to end up with data that's highly correlated between these ground truth factors. And we want to still achieve disentangled representations, even in the presence of these correlations. So here I'm showing you an example, very basic example. This is still the cart pole that we saw earlier. And let's say there's two different factors of variation that we just show in this example. One is the color, for example, blue or green, and one is the shape of the object. For example, on the top row, you have a smaller body and a longer pole, and the bottom row, you have a bigger body and a shorter pole. It changes the friction coefficients, it changes the optimal policy. So if we train where most of the time during training we're exposed to this combination on the diagonal here, in the red diagonal, most of the time, let's say 95% of the time, then by assuming independent factors, because the color and the shape of the object are now highly predictive of one another, you force the representation to collapse them into one dimension, and then if one thing changes, you screw up the policy again. So you're in a similar situation to what we had before. But what we really want to have is, for example, if we train this environment, we want to understand that these things are distinct factors that just happen to be correlated here. And if now, for example, we change the color from blue to green, we can still transfer the optimal control. So basically, if we now reverse the correlation, and after training, we get exposed to different combinations that we rarely ever experience in training. The blue diagonal here, we want to be able to gracefully go from left to right or from top to bottom without losing performance. And that came out in a Nero's paper last year. So we want to be able to learn this. Again, there's not a lot of technical detail. I just want to share with you the main idea, which is that there's this thing called conditional mutual information. And it turns out that you can build an auxiliary loss that actively drives that to 0 with an appropriate conditioning set, and then you can actively achieve disentangled representations in the face of these correlations. So what I'm showing here is an example. This is from an MDP, Markov decision process, which probably everyone knows. These are the states and the actions and so on. On the right end, in the green circle, these are the representations Z that we want to learn. And I'm just showing you 2 dimensions as an example, just to keep it small. They, in reality, will depend on the state features, but we don't get to see them. But what we show theoretically is that if you condition on a conditioning set that includes the previous actions and previous representations, then theoretically you actually have sufficient information to learn the disentanglement. And in practice, it turns out you actually only have to use a small window of that to get close enough. So basically, we use conditional mutual information with this conditioning set, and we constructed a auxiliary loss, again, that can be combined with reinforcement learning algorithms to drive that to 0. We call this CMIT, conditional mutual information for disentanglement. It can be used with any RL algorithm, as I showed you before. And again, we tried this in a range of different control tasks in different environments. Here I'm showing you 4 examples from the DeepMind control suite. On the left, you have your inverted pendulum again. Then you have your walker. Then there's sort of flipping task and a jumping task. There's a whole range of things you can play with. And what I'm going to show you in the next slide underneath these images is a similar plot to what I showed you before, where there's training going on, then there's the vertical line where there's a sudden change in the environment, and then we have to recover from that change, or just gracefully transfer through that. So it looks like this. Each one of these plots corresponds to the control task above, where on the left half we have our training environment with the red diagonal that you saw earlier. And then at the vertical line, we flip it to the blue diagonal that I showed you. And what you see is a bunch of different lines that correspond to different state-of-the-art algorithms. And you can see that once they do a bit of training, and then they get to this middle line, and they break down significantly. And then they have to recover. In some cases, they're not even able to recover. But if you look at the green line, which is an algorithm that uses our CMIT loss, you see that it's almost not affected at all by this change. It very sort of gracefully steps over that, and it's nearly not affected. So that, I think, is the kind of robustness that we require in reinforcement learning to make it practical. So we just can continue through that change, and we can continue to operate normally. Here's an example video to show you what that looks like. So this is for zero-shot transfer, which means it's the point in time when the vertical dotted line happens. We're now taking the policy from that point in time, and I'm just basically showing you what happens when you do not use the loss versus when you do use the loss that we developed there. Okay, so first, we do not use the loss, and you can see there's the 4 different sort of correlations that I showed you earlier, and you can see that it's messed up the policy, right? So even in the training set, it's doing weird stuff, but in the blue diagonal, you can see that they're completely giving up. The policy is unable to do anything useful. Now, if you use our loss and combine it with the SAM algorithm, you can see that from left to right, it's transferring exactly the same walking gait that it's actually learned in the training set. It's not affected by this change in significant change in the correlation. You can see it's the same type of walking that is unaffected by these changes. So it's a nice kind of robustness that we were able to achieve here. And of course, you can continue to train and polish it a little bit more, but in this case, that wasn't even required. Okay, so now just one more teaser. In the latest iteration, we just had a paper accepted at one of our papers at the new RLC conference, which is this year. Now it takes us to an application where we're training a robot to use multiple cameras, and it's learning to disentangle the inputs from the camera so that you can downstream specialize to any one individual camera angle. So it looks like this, just a teaser. Here we have an example control task where there's a first-person camera and a third-person camera, and you train specialized policies. You can see that on the left, that kind of works, but on the right, the third-person angle is actually not providing you with information to solve that task. And now we can do something else. We can train with both of these images, videos, and then we do a zero-shot specialization into any one of these cameras, and you can see that we can actually achieve that. So we use disentanglement again, where we disentangle the shared representation and the individual factors from the cameras. So it's just a teaser. Please check out the paper if you're interested. Okay, brings me back to this home slide. This was the first idea, disentanglement. Now I'm going to move into the multi-agent part, which is where we do a lot of work. A lot of our early work started here. Okay, I'm going to jump right into a paper that I think is a really nice story. This is from, I think, NeurIPS 2020 or 2021, one of those years. And the idea is now that we don't have not just one actor, we have multiple agents that exist in a team, and they need to learn collectively how to collaborate, how to achieve their tasks by taking actions in a coordinated way. So I'm showing you some examples here, where on the left you have a toy warehouse example where there's shelves and you have your agents that need to collect shelves and bring them back to your workstation. Then there's a StarCraft 2 environment where you have these Marines that need to shoot each other and various kinds of tasks like that that you can scale up. What we add to this challenge is that we make them sparse, which means that almost all of the time the agents get a 0 reward, and only in very few defined moments when they've achieved some kind of milestone will they get a positive reward. So for example, in the StarCraft example, they only get a positive reward once they've destroyed the enemy team. And until that point, it's 0 all the time. Makes it really hard to learn. And especially since it's multiple agents that coexist and learn together. Okay, so how do we do this? What I really like about this work is this is a very basic, simple idea that leads to some really strong empirical results, and it's easy enough for us to do theoretical work on the soundness of the gradients and so on. So I'm showing you an example application here just to keep it simple. This is a grid, okay, where we have 2 agents. There's the blue agent and the green agent, and their task is to get to the center point at the same point in time. They get 0 rewards all the time until they get to the center point, then they get +1. So even though it's a very basic toy task, you can already see the exponential growth here in the search space. It's actually not that easy after all. In the standard multi-agent RL paradigm, which is called independent learning, everyone uses their own off-the-shelf single-agent RL and their own data. And then, for example, the blue agent, you use the blue trace, which is the blue dotted line, and you use that to construct your gradients, whatever, and then you update your policy. You don't use the other stuff from the other agent. So the observation in this work was that, well, the other agent is kind of doing a closely related task. Maybe there's an opportunity that we can learn from one another and we should share these experiences. And that's the whole idea in a nutshell. Basically, what we do now is we share experiences. The green agent now, in addition to its own data, it also uses the blue agent's data by basically putting itself into the shoes of the blue agent. But that makes the data off policy. It comes from a different behavior policy. There's a distribution shift. So we correct for that by doing a basic importance sampling step. In this case, we used a vanilla importance sampling. You can do more fancy stuff as well. And then you use the data combined to construct a more robust local policy gradient. That's the whole idea in a nutshell. Okay, so again, I'm going to jump right into some results to show you what this looks like. We tried this in a number of environments and a number of different tasks. Here's, again, sort of a small StarCraft example and the warehouse example. First, let me explain what the axes and the lines mean. This is for the StarCraft example. The green line SERC is ours. This is shared experience actor critic, where they share data. The orange line SNAC is shared network actor critic, which is when there's a single model and all the data goes into that one model, and every agent uses the same model. And then there's IAC, independent actor critic, which is the standard thing that I mentioned, where everyone uses their own data and their own learning. There's no sharing of anything. So it looks like this. You can see that the other 2 guys completely fail, and simply by this simple act of sharing experiences, we are actually able to solve this task. And similarly for the other tasks as well, you can see that we learn very fast, almost as fast as putting all the data into one model, but we arrive at a much better local optimum in the joint policy space. And in the paper, there's a lot more results about bigger environments and comparing against state-of-the-art and so on, which are much more complicated, and we actually achieve the same performances, or even better than super complicated state-of-the-art algorithms, simply by sharing experiences. So instead of showing you that, I want to just show you some interesting analysis. What's actually going on? If you share experiences, you might expect to learn faster. Okay, that's kind of intuitive. But what's maybe not so intuitive is why you would end up in a better local optimum. For example, the green line ends up in a much better place, right? So why is the fact that we share experiences enabling us to do this? It's not so straightforward. So we looked at an example to analyze what's going on. What I'm showing you on this plot is basically 2 green lines, which corresponds to the individual agent returns of 2 agents that use our sharing algorithm, and then 2 blue lines, which correspond to the individual returns of 2 individual agents that do not share anything. And so what you can see when you look at the blue lines, there's this red line that I put in there that shows that there's a sort of discrepancy in the learning speed. Typically what happens if you do not share is that one agent begins to become competent at doing something useful, while the other agents are lagging behind a little bit. And what can happen is an interesting dynamic. The more competent agent begins to deprive the other agents from receiving the necessary experiences in order to catch up. It's already doing a lot of heavy lifting itself, basically. And in contrast to that, by sharing experiences, we enable the agents to sort of have a uniform learning progression. No one is left behind, so to speak. And I think that's a really interesting result. It enables them to learn faster, explore more effectively, and end up in a better space in the joint policy space. So I think a lot more could be done to really find out what's going on in the learning dynamics here. Okay, here's just a video to show you what this looks like in practice. This is in the StarCraft task. We control the team on the left, where we have agents for the individual units, and then the other one is AI bot. You can see that the first thing they learn is to spread out to maximize fire patterns. Then you can see the healing unit at the top is focusing on healing the high energy assets, which prolongs his life. And then you can see we've sort of outflanked the opponent. And basically, we now are taking down one after another. And keep in mind that there's 0 rewards almost all the time. Okay, so this is a really hard task. We did not tell the agent what to do. It's learned all these strategies on its own. Okay, just to wrap that up, I think there's a nice slide here where you can think of this as a spectrum. On the left end, we have no parameter sharing, which was the blue line. Everyone does their own stuff. No one shares any experiences, okay? And so the benefit is that you can differentiate behaviors, but it's slow, it's not efficient, and it doesn't learn as well. On the right end, you have parameter sharing, which is the orange line. Okay, so there's one model, everyone uses the same behavior and puts all the data in there. It's cheaper, it's smaller, it's efficient to compute, but the fact that everyone uses the same model means they cannot differentiate the behaviors when they do the teamwork, which is a problem. Typically, there's roles they need to fulfill. The thing I just showed you is somewhere in between here, shared experience, actor-critic. It is still no parameter sharing. They have their individual models, which allows them to differentiate behaviors. But they do share experiences, which allows them to learn more efficiently. But there's still a drawback, which, for example, is the number of parameters, because they have individual models. And so in another paper that came out in ICML, I think in the same year or in the year after, we actually showed that there's another trade-off you can achieve by enabling the agents to decide for themselves with whom they should be sharing parameters and maybe with whom they should not be sharing parameters. So I'm just going to leave it at that. And I think this is an interesting spectrum you can think about. And please have a look at the papers. Okay, coming back to the slide. And now the last vertical I want to share with you is all this work we do in industry applications. We do a huge amount of work working with various sectors to develop RL applications and autonomous systems. I'm just going to show you 2 examples. One is for warehouse automation, where we use multi-agent reinforcement learning to optimize, for example, an Amazon warehouse. And the other is a company in self-driving in the UK that was involved in, that was later then bought by Bosch. Okay, starting with the warehouse automation. We work with Dematic. Dematic is a gigantic intralogistics and warehouse automation company. They operate everywhere, Amazon warehouses, other warehouses. They create these huge robotic systems doing automation and so on. But basically, the application that we want to build with them looks more like this, where imagine you have a warehouse, okay? There's a lot of aisles with a lot of shelves, with lots of items, different levels and so on. The classic approach would be that you have a bunch of humans that work through the order profiles. Your Amazon order comes in, different items, different quantities. The humans get to go to the right places, pick the right items, bring them back to your workstation. And so that's inefficient for a whole range of reasons. There's a whole business case behind this. And so what we want to do is now we want to throw in AGVs, or mobile robots, basically, that coexist with the humans. And the humans still do the picking, but the AGVs now have to service the humans, have to support them as much as possible by being at the right place in the right point in time, so that humans can just sort of offload their cargo, basically. Then the robots bring it back to the packing station and then go back to the warehouse. So we use multi-agent reinforcement learning to optimize the policies both for the humans and for the robots to maximize the KPIs we care about, which is order throughput. The interesting question here is, basically they gave us a challenge. When they build these kinds of systems, they have a huge amount of engineering effort. They have these 2 main approaches. One is called follow me, which is when every picker has a bunch of AGVs that is sort of assigned to a picker and they just follow them around. Or pick, don't move, which is when the pickers get assigned to particular zones in the warehouse. And then the AGVs move around freely and they have to decide sort of who to service. And then you can do traveling salesmen's problems and so on. But the problem with these heuristic approaches is that they're brittle. They require a huge amount of engineering effort for whatever the warehouse configuration is, and a lot of tuning as well. And sometimes one works better than the other, and they have to find that out. So it's not ideal. the challenge we got is basically, can we develop an automated way to derive optimal joint policies purely based off the blueprint from the warehouse? And that's basically what we've been working on with them for a couple of years. First, we built this high-fidelity simulator with their engineering team. This is a simulator that can take different vehicle models, can take all the customer data, has high-fidelity dynamics and so on. We can represent all kinds of customer warehouses, for example, small, medium, big. Then there's this joint warehouse, which means there's a cold compartment with cold stuff and a warm compartment, and so there's just this narrow channel in order to maintain the temperature. So they give us basically whatever they have. Customer comes to us, gives us a blueprint, we put it into our simulator, push a button, and basically maximize as hard as we can the performance of these agents in these environments. There's a bunch of things that go on here, but if I was to sort of take out the main idea to present to you, it would be this idea that we're building a hierarchy with a manager agent at the top and these worker agents at the bottom. So the manager agent, you can imagine, is sitting at the top, gets to see the whole warehouse. And its task is to learn a policy that is dynamically sort of creating and allocating these tasks to the worker agents. You go here, you go there, you do this. And then the worker agents at the bottom, which are the human pickers and the AGVs, they need to learn how to execute these tasks as efficiently as possible whilst they coexist with one another. Okay, so this is coordination going on. And we basically develop multi-agent reinforcement learning algorithms that optimize the policies of both the manager and the workers simultaneously. So I think it's a really cool idea if you think about it. There's these two things that coexist, and they need to learn how to create tasks and how to execute those tasks at the same time. So that's, in a nutshell, the high-level idea. Some results. So there's these 4 plots that correspond to the small, medium, large, and disjoint warehouse that I showed you earlier. First, there's the vertical lines, which is purple and gray. That is the 2 heuristics that they use. There's no learning, so that's why they're horizontal. And one thing you can see is that sometimes one heuristic works better than the other. It depends on the specifics of the warehouse. And then there's these other lines which are learning. These are sort of specific multi-agent reinforcement learning algorithms that are designed to optimize this manager-worker hierarchy. And you can see the first thing is that we outperform very significantly these existing heuristics, which is a big deal for them, right? It means money. It directly translates into money gains for them. But also, we are not affected by this idea that sometimes one thing is better than the other. Whatever is the best thing to do, the algorithm will figure out. And I think that's a really cool thing, right? So you can give us this profile, and we create the ideal looks like this in practice. So this is one example where the orders keep coming in. There's this endless stream of sort of Amazon orders coming in from the internet, and then they swarm out and they begin to operate by picking items, retrieving them from the shelves, bringing them back to the workstations, and so on. So it looks kind of like more like a busy beehive. As a result of this work, this is now firmly embedded in their commercial pipeline. They have a real-world prototype they're building in Germany in a sort of reproduced warehouse. And hopefully in a couple of years from now, if we can continue on this trajectory, we can make a claim that this is the world's first real industry-scale application of multi-agent reinforcement learning, which I think is really exciting. And we were able to share some of the results as well. If you would like to take a look, please have a look at this paper here. Okay, and the second thing I want to share with you is a business that I was a part of until recently called 5AI in the UK. So here at the start, the idea was that we wanted to build self-driving vehicles from the ground up with everything you need. We call this a stack. So there's perception planning, prediction, control, and in the later years we had to focus on simulation and testing. The company started in late 2015, quickly became a leading startup in the European space, and we were the lead partner in a UK-funded urban road trial in 2 boroughs in London, where we were showing our fleet basically. And the company itself has a bunch of different offices. The office that I'm a part of in Edinburgh is specializing in motion planning and control. And as a result of this, the company was bought by Bosch in 2022 and is now part of this gigantic Bosch family. Okay, so this is what it looks like in one of our vehicles. This, I think, is from 2020. There's the safety driver, who is not touching anything, but has to be there to disengage the vehicle if it's required. There's also a safety engineer sitting next to him who looks at a bunch of laptop screens to check out the data streams. And here's the same view, but from the vehicle's perspective, where at the top you have your fused image, and at the bottom there's just 2 cameras stereo feeds, one pointing forward and one to the side. And basically you can see that we are navigating, we're getting closer to a roundabout situation. There is a lot of detections going on. You can see in the bounding boxes. You see that it's a bit busy, so we have to give way. Now there's an opportunity to merge in, which we then do. Then we exit again. zebra stripes coming up. There's no one standing there, so we can continue along the local trajectory that you see on the video overlay. And this was actually a very straightforward situation. There was not a whole lot of complication going on. But the reason why I want to show this is because it shows how complicated this is. There's so much going on, really. There is basically, the way we decompose this is that there's sensing and fusion, right? We need to make sense of the environment. There is localization, which is to understand where we exist in this environment. Detection of the other entities. Tracking where they're going can be surprisingly difficult in these environments. And then there's prediction and planning, which is the work that we focus on in our team. And also a control, which is when we synthesize the plans back into the low-level control. So we operate mostly in this space, and one of the cool things about this business is that we did a huge amount of research publishing in ICRA, IROS, and IEEE venues. So focusing on, our team was focusing on prediction and planning, the other offices focused on other elements. For example, we did trajectory prediction, a classical control problem. We did goal recognition, which is when you want to make sense of what someone else is up to, depending on what happened in the past. We did optimal planning, and also we did some amount of work in explainable AI, which is now really important. So unfortunately, I don't have time to tell you about all these works, but I can point you to our website, which lists all the papers. And also I want to point out one recent paper that we brought out, which is a survey paper about explainable and trustworthy AI in these safety-critical applications. So please have a look and check it out. Okay, so that brings me to the end of the first part. I just want to give you some adverts, some resources that I think could be useful, especially for PhD students. The first is in our university group, we have this blog where we provide all kinds of sort of tutorial-style articles. For example, we have a blog post about tips and tricks for deep reinforcement learning. There's so much you need to know about. Really, it makes a huge difference. But doing this yourself is kind of a pain, so you can check out the blog post. I explained disentanglement earlier. There's a tutorial on the blog. We have a new paper in ICML about unsupervised environment design, which is another way to robustify policies, and so on. There's quite a few things. And in addition, we have these many code repositories, but the most important one is called ePyMAL, Extended PyMAL, which is a research prototype framework for multi-agent reinforcement learning. That's now widely used by the community, and it comes with mature implementations and standardized interfaces. So if you want to get into multi-agent RL, and you just quickly want to run some stuff and get some numbers, you can use that quite easily. And the second resource is a new book that I just finished writing with my two excellent co-authors you can see here. This is I think the first ever written book about multi-agent reinforcement learning with MIT Press. You can get the PDF for free on the website there. Or if you want to help us live a more luxurious life, you can pay for it as well. You can get it off Amazon now. The book is designed to be self-contained, so it has chapters on single-agent RL, game theory, models and solutions, deep learning, single-agent deep learning. It takes you sort of step by step, and then it gets into all the multi-agent reinforcement learning stuff. So it comes with a code base, again, which is designed to be for beginners. It's easier, and it comes with slides in case there's professors here who would like to teach this. So you can get the PDF now, or you can get the print in December. Okay, so now I'm moving on to the next part, which is about LLMs. Right, so in this first part, I showed you some sort of interesting ideas, disentanglement, experience sharing, hierarchies and applications. And now we want to look at LLMs, which is this new big thing that's coming up. How can we do that? How can we use LLMs to develop capable autonomous systems? Okay, so this is one recent work that we submitted just now to IROS. Where we develop basically an LLM-based agent that does interesting tasks. Okay, so LLMs, I think everyone knows what this is by now. It's all over the place. There's an interesting history, lots of people looking at all kinds of applications. I'm going to skip over this, but instead what I'm really interested in is LLM for robotics, for autonomous systems. And there's a few reasons why that is interesting. One is they have this ability to understand task descriptions from natural language. And they have this ability to understand feedback in natural language as well, which is important if you coexist with the robot, right? You can have this natural interface. There's this idea that they come with a bag of common sense knowledge of the environment, and hopefully that tells it what's a plausible action versus what's not a plausible action. And basically, we want to see if we can use this to produce plans that we can execute. Okay, so we started doing this for this housekeep task, which is where you have an apartment. There's a bunch of rooms, different kinds of rooms, like you would expect, and it's messy. There's all kinds of things flying around, and there's this one robot, which is basically existing in this environment and has to clean up the house. Okay, so basically you have to find the various items and bring them into their desired locations. Cleaning up the house, basically, housekeep task. And there's this whole simulator you can use for that. The robot, basically what it gets to see is a pixel image. It gets to see depth and segmentations, as you would expect from a real robot system. Okay, so this is challenging because it requires long horizon planning and partially observable environments. And it also is challenging because these items could be anywhere. There's this combinatorial growth in terms of items and where they ought to be. But in addition, what we're interested in is that these things should be personalized. Okay, so different human users might have different preferences in terms of what constitutes a good location for a coffee mug, for example. So a single pre-trained LLM might not be, even though it has this common knowledge, it might not know exactly what these user preferences are. So we want to have these systems that can also understand user preferences. And basically that's what we did. We developed an LLM-based sort of autonomous systems that can solve this task and take into account user preferences. The pipeline you see here, at the center there's the LLM planner. This could be anything you have access to. Then it takes as input a prompt. I explain that a little bit more in a second. It produces a high-level plan, which is various steps you need to do. They get passed on to a lower-level controller to execute the lower-level controls, and then you have your loop, basically. Kind of similar like reinforcement learning. And in addition, we have this machine learning pipeline where we use human preference data to fine-tune the robot, basically to match these human preferences. So basically, it's a combination of imitation learning and also reinforcement learning. But I'm just going to keep it at that in terms of technical depth. Okay, so a little bit more about the prompt engineering. First, there's the thing what we call context. It consists of a household state graph that describes the spatial relationships. There's the instructions about what we want to achieve. Put this item there, put this item there. And then there's the examples we want to give into the prompt so that the LLM knows what kind of output to produce. Okay, so this graph we produce in a pretty straightforward way. We start with an empty graph, and then as we explore the environment, we get to see these different rooms, and then we create new nodes that correspond to these different locations and objects and receptacles and so on. So we build up the graph iteratively. And then next, we give it basically the task instructions. What you see here now in the yellow bounded box is the whole prompt, basically, where at the top there's the natural description of this graph with the spatial relationships. Then in the blue part, there's the instructions, put this there, and then at the bottom there's a couple of examples for the kind of plans that we want to see. Okay, that's what we do in the prompt engineering. Once it takes that, it produces an output plan. For example, what I'm showing here is step 1, go to pan 1. Step 2 is look at pan 1. So it's sort of a sequence of tasks you have to execute. And these tasks are executed by these low-level controllers. Okay, the next thing is this user preference fine-tuning. As I explained earlier, we have this two-phase machine learning pipeline where we use basically user preference data to fine-tune the model. But let's look at some experiments. Okay, so here's 4 different apartments. We have success rate, which means how many objects are in the right location. We have an LLM model. In this case, we used a GPT 3.5 Turbo. This is what we had access to. And we have a bunch of different sort of user configurations, just a low number, actually just 10 tasks in this case. Here's a demo video for one particular task, which is when you have to pick up the sweetener from a desk. So first, you explore the environment. You create this graph, which is the spatial relationships with the items in the rooms and so on. Then you have to find the right object in the right room, which is the sweetener. You now found it here as the white thing on the table. You look at it, you zoom in, you pick it up, and then you navigate to the correct location where it ought to be deposited, which is up here. And the interesting thing is that we get all this for free, basically. We get this for free from this LLM, basically, with a little bit of fine-tuning to know what the user preferences are. Okay, and in terms of quantities, it looks like this. There's some baselines, and then at the bottom there's the various ablations, but basically it's our method. Scene 1, 2, 3, and 4 correspond to the 4 different apartments, and you can see that in terms of success quantities, we are much higher than these pre-existing baselines. And again, this comes basically for free from this LLM agent, which I think is interesting. Okay. In summary, if you want to check out the paper, please have a look at the archive submission here. But now I want to use the last 5 minutes to share some observations from this work about why I think we need to walk away from LLMs and do something else. Okay, so we did all this work, we spent quite a bit of time, and we had all these observations, but there's 3 observations that I think are kind of interesting. And you can let me know if you disagree, okay? So the first observation is, all these papers that we have seen in the past 3 years, maybe 20 papers or so, they basically all instantiate the same general recipe, which is at the center there's this LLM. Okay, we use GPT 3.5 Turbo. Then there's a huge amount of engineering effort going into this prompt engineering, where a bunch of guys come up with clever choices for this prompt that goes into this LLM. And then similarly on the other side, there's this planned post-processing. Whatever comes out often is kind of not quite right. You have to fix the reference labels, you have to fix the sequencing, you have to decide which pieces to extract. So there's a bunch of work there as well. And then in between, there's this fine-tuning going on, which is supervised learning or reinforcement learning, or in our case, we did both. Okay, so I think from what I can tell, the majority of the literature instantiates this recipe, and as did we as well. But if that's the case, then whatever the claims are that these people produce, I think they will be really brittle, because they will depend crucially on the LLM at the core of the system. If I swap out the LLM, can you tell me whether or not your claims will continue to persist in this new environment? Maybe they break the LLM. Maybe the new LLM doesn't care about your stuff anymore. Maybe it doesn't require it, and so on. Maybe it could make it worse, could mess up the parameterization. So I think that feels a little bit dissatisfying, right, in some sense. It makes it brittle. But the next thing, which I personally find is the most important observation, is that LLMs are not natively designed to maximize objectives for optimal control, which is what we really care about. They are designed to maximize word token prediction based on the internet text, okay? But I would say that's really not the same as these control theoretic objectives that we care about. For example, maximizing expected discount return. This is something that we can write mathematically and we understand. We can develop algorithms that rigorously converge to these things. But whatever your LLM demonstration is doing, even though it looks cool, I'm pretty sure if you were to write that down into a control objective, it would not match this thing that we care about here. And it gets even more complicated in multi-agent RL, where we now have a joint policy, and they need to be mutually optimal with one another. It gets really quite complicated. Again, I think we would not end up with something like that. Okay, so where do we go from here? Some directions I want to share. We could continue to do this general recipe that I showed you. We chase constantly after the latest LLMs, and then we hope that whatever we come up with will continue to be useful in the next year when the next big thing comes out. Probably not, and it's probably not very satisfying, and we have decided in our lab that we're not going to do this kind of game anymore. The second thing is you could do fine-tuning of LLMs, right? So a lot of people are looking at this, and we looked at this as well. You can try and fine-tune pre-trained LLMs to get a little bit closer to what I just explained. But then there's the question, how does this mask their internal knowledge base and so on, which is the thing that we really care about? How does this limit their generality, which we care about? How much additional training is required, and so on. So it's quite a few questions. I would say maybe it's more interesting to just dump LLMs. They're not designed for what we care about, and instead create this new thing, large decision models or large control models. So these things would be natively multimodal. They take not just text, they take also vision, tactile, other motor sensing, and so on. They have a much more holistic perspective of the environment. And that I think we ought to be doing, but then the question is, where does this data come from? We have the internet, which comes for free. Basically, we have all this data, but we don't yet have an internet of control data. So that is going to be some really heavy lifting. There's now businesses in the US and in China where they have a lot of money to create this data and curate it. There's also open access sort of initiatives where they're trying to do this a little bit slowly, but I think we need to do this heavy lifting to get the data. And then also, how do you train and scale and make this robust and so on? Lots of open questions. But I think that is possibly a much more interesting and exciting direction to explore rather than instantiating this general recipe. Okay, so with that, I want to thank you very much for your time. Really appreciate it. Please go check out our website for these various resources and the book as well. If you happen to be in China in a few weeks, you can meet me there as well. We'll be at a bunch of universities, and also there will be various summer schools where you can meet me. So thank you very much for your time, and happy to discuss.